Right, hi everybody. So this question has given us a function, its first derivative and its second derivative, and we're being asked to essentially walk through the procedure of sketching it. Okay, so before we get into these little pieces right here, as I've done before here, what I want to do to take first of all is to take a look at the domain, because that is going to have an impact on the work that we do here. So let's just take a look here. X squared e to the x here. What is the domain? Well, I've got two different functions multiplied together, so the domain is going to be the overlap of the domains of those two individually. Okay, well, the domain of x squared is all reals, okay, so that's not a problem. But it turns out the domain of an exponential is all reals as well. So it turns out this particular function actually doesn't have any issues anywhere. It's defined for all values of x, which is good, okay, which is good. That makes things a little bit more straightforward for us. So to start off with, I'm being asked to find the limit as x goes to positive or negative infinity. So I guess I'm looking for, I'm looking for asymptotes here, if there are any here. So let's take a look at positive infinity, x squared e to the x. Well, individually, x squared will go to infinity and so will e to the x, which suggests to me that at the right-hand side of this graph, it's just going to shoot off to positive infinity. Now, if you take the limit as x goes to negative infinity, though, I didn't throw the negative in there. As x goes to negative infinity, x squared e to the x. Now, if you plug that in to x squared, negative infinity will become positive infinity, okay? And that makes sense. The parabola goes off to infinity in both directions here. But the exponential function won't, okay? When you plug negative infinity into this, remember that that's going to cause, well, okay, your exponential function looks like this. This might be a better way to say it. And if you go to the left here, this is going to drop to 0. Now, you can figure this out if you'd like, just by playing with your calculator, plugging in values and experimenting with this. But an exponential function, its behavior at the extremes, okay, is actually quite extreme. And so what happens here, when you multiply those together, this is going to dominate. This is going to drop closer to 0 faster than this increases. And so what will happen here is this will be the dominant expression here, the dominant factor. It's actually going to go to 0. And I know that's not abundantly clear when you look at that. I mean, it's not obvious when it jumps out at you. But again, my comfort level with this and with these functions is maybe a little bit higher than the average students there. Not every student, though. There are students out there that are far more comfortable with this than I am. But if you're kind of looking at this and you're relatively new to it, you will see that these exponential functions are really, when they appear in an expression like this, they are dominant functions here. They will really determine the way the values kind of pan out. So that's the one that's going to control this at the extremes. Now let's take a look at the critical numbers. And this has to do with the derivative, the first derivative. And so what we do is we look for either where the first derivative is undefined in the domain, and it's not. Okay, there's no value for x where this would be undefined. So I'm just going to set the first derivative equal to 0. And I'm going to try to solve this. Oops. Now, I like this chapter because of the functions that we work with. They're a little intimidating looking, but if you just take a quick look at this, I can factor out an x and an e to the x out of this, and I'm left with 2 plus x right here, okay, equal to 0. Now, where does this go to 0? Well, when x is equal to 0, it's going to become 0. E to the x, though, never does become 0. And what I like about this is it becomes a factor, and so I can take it out here, and when I look at it, like it never does become 0, so that's not even a concern. So, but I can also get a 0 here if x is equal to, whoops, sorry, I was going to write x is equal to, but I've got a comma there, so I'll just put -2 there. So here are my two critical values. Okay, possible maxes and mins. Now let's take a look at possible points of inflection or cusps here. So we're looking at the second derivative. And we were given the second derivative, just like we were given the first derivative. That's a little bit more involved as an expression, but that's okay. I'm going to factor out my e to the x here. and I'll be left with 2 plus 4x plus x squared, which I'm going to just rewrite in order, because I like that better. That looks better to me. Now, where does this become 0, or where is it undefined? Well, it's not undefined anywhere, so I'm not going to get any points of inflection or cusps because of that. Where does it go to 0? Well, it doesn't go to 0 because of e to the x, that's for sure, because e to the x won't. But x squared plus 4x plus 2 might. Now that's a quadratic. If you take a quick look at it, okay, we're going to try to figure out where that goes to 0. Now, it shouldn't take you too long to realize that's not going to factor. So I'm going to have to use the quadratic formula. So, and yeah, and I can almost feel people on the other side of this groaning like, oh, why? That's okay. That's okay. It's not going to take us long to get through this. So negative b plus or minus the square root of b squared, which will be 16, minus 4 times 1 times 2, all over 2 times 1. Okay? And so this will be negative 4 plus or minus the square root of 8 all over 2. And this will be negative 4. I'm going to simplify that radical. 2 root 2 all over 2. And so here we get negative 2 plus or minus root 2. Okay, and those are my two possible values for my points of inflection. But to determine what's going on here, what we got to do here is we got to take a look at our intervals of increasing and decreasing, so C. What's nice about this is there's just the two. Like there's no asymptote there, vertical asymptote for me to worry about, so it's just these guys right here. And it's actually fairly easy to figure this out. If you pick a number that's less than negative 2, okay, well, our exponential functions here are always going to be positive. This term here is going to be positive. This one will be negative. Okay, but because of that square, so they've both got an exponential, but this one's also got a quadratic here. It's going to grow faster than the linear, so this is going to be the dominant one, and it's positive. So that's going to be positive right there. And I can do that, I can make that kind of argument because I'm talking about the interval from negative 2 all the way back to negative infinity. So I can plug in like really big numbers for x. When I look at this interval, I can't just do that as willy-nilly as I did here because I've got a very limited interval that I can work with. Let's pick a number like negative 1 in here. E to the negative 1, e to the negative 1, that's going to be positive. This will be negative. This will be positive, but it's only going to be 1. So it turns out that this now becomes the dominant value. That's going to be negative there. Now, once you pass 0, everything is positive, so everything's positive. Okay? I don't know how else to say that. So this is going to be increasing on negative infinity out to negative 2, union 0 out to infinity, and it will be decreasing on negative 2 to 0, and that's it. Now let's take a look at our intervals of concavity, and similar to the intervals of increasing and decreasing, we've really only got the 2 to worry about. Whoops, sorry, I wrote that too quick. That will be negative 2 minus root 2 and negative 2 plus root 2. Now it's important to remember that both of these will be negative. Okay, root 2 is smaller than 2. So, I mean, negative 2 minus root 2 will be negative. But because root 2 is smaller than 2, negative 2 plus root 2 is still negative. Now you're going to see why that's significant in a moment. If you go up to your second derivative and pick a number that's less than negative 2 minus root 2, and we can go way far back, like negative 1,000,000, right? Negative 1,000,000. This will be positive because that exponential function always is. This will be negative. Okay, because of the 4x, but if I choose negative 1,000,000, that's negative 4,000,000 multiplied by the exponential. Here, this is going to be negative 1,000,000 squared multiplied by the exponential, and that is going to dominate. So over here, this is going to be positive. In between these two, and you can pick a number like negative 2, because just think about that. This is negative 2 minus root 2. This is negative 2 plus root 2. Like negative 2 is right smack dab in the middle. This will be positive, okay, because it always is. This will be negative 8 times the exponential. but this is going to be positive 4 times the exponential. So this is going to be the dominant function here, and it'll be negative. And then over on the other side here, we can go as far as we want to the right, pick a really, really big positive number. Everything becomes positive. So this expression here is going to be concave up from negative infinity out to negative 2 minus root 2 union negative 2 plus root 2 out to infinity. And it's going to be concave down, negative 2 minus root 2 to negative 2 plus root 2. Okay. The next part here was to find, that was D, I suppose. We're going to find the exact coordinates of our maxima and minima. So we have a max at x equals negative 2. And if I plug that in, I'm going to get negative 2 comma. That looks like when I go up to my original here, negative 2 squared is 4. E to the negative 2 will just be 1 over e squared. So this will be 4 over e squared. And I will have a min at x equals 0. And that's just going to be 0, 0. I mean, there's an x squared out in the front, so it's just going to be 0, 0. F, concavity, the points of inflection. Now, I've already gone through and established this. The question asks for them in exact form. Not entirely sure why. That seems a little cruel, because our points of inflection, if you throw those in exact form, we're going to be negative 2 minus root 2. Okay, now I got to look, I've got it up here. Comma, this is going to be 6 plus 4 root 2 multiplied by e to the negative 2 minus root 2. Which is a little intimidating. But anyway, whatever. Negative 2 plus root 2. This is going to be similar, but 6 minus 4 root 2 e to the negative 2 plus root 2. Sorry, and I'm just kind of jumping us through that real quick, because all I'm doing there is taking these x coordinates and plugging them into here. Just bear in mind, though, that this is squared. So when I take, for example, when I plug negative 2 plus root 2 squared into that, that's negative 2 plus root 2, negative 2 plus root 2. And when you multiply that out, please remember to do this. That's going to be 4 minus 2 root 2 minus 2 root 2 plus 2. Please remember those middle terms. That's where I'm getting this, this coefficient from here. Now, to sketch this, whoops, we know that we had that horizontal asymptote, at least we did when we went this way. We saw that we had a maximum at negative 2, 4 over e squared. We had a minimum at 0, 0. That's the convenient one. We had points of inflection. Now, I'm going to let you know, when you compare them to these points right here, I'm just going to, if you get the decimal values, they're going to be approximately there. Now, that should give you a really clean idea of what this graph is going to look like, particularly because when you look at the intervals of increase, it's increasing here, decreasing here, increasing here. It is concave up here, down here, up here. So we've got this asymptote to the left, so it's going to slide along the x-axis. It's going to increase, concave up, point of inflection becomes concave down to a maximum. Now it's decreasing, concave down, point of inflection. It's still decreasing, but now concave up, hits a minimum, and now it's increasing and concave up forever. And that's what your graph is going to look like.